Hello students, welcome back to online classes of digital communication. So there was a long gap after vacation. I think this is the first class we are going to see. I hope in the last class whatever we have discussed, that was clear to people. So before moving to the class, I think so many students and so many people have seen so many tough times in the last few days. So we hope inshallah the upcoming days will be much better for everyone. We pray for that one. So now in today's class we are going to see our next topic is our adaptive delta modulation. So before we move on to that topic, I would like to just revise what was the last topic we have discussed. So in the last topic we have seen about your delta modulation, right? These were the different kinds of pulse modulation schemes. So we have pulse code modulation we have seen, then DPCM delta differential pulse code modulation we have seen, then after that we have seen delta modulation. Then in next topic that we are going to see in today's class is your adaptive delta modulation. So before we move on to the adaptive delta modulation, what was your delta modulation? So if a PCM transmitter, it actually does that it will be transmitting all the bits at once, right? So PCM transmitters will be allowing all the bits which are used to code that particular sample. So all bits are sent at a time. So hence the signaling rate as well as the channel bandwidth will be quite larger in that case. So in your PCM. So as to overcome that particular problem, we are going for your delta modulation. So what is the delta modulation working principle is? So it will be transmitting 1 bit per sample. I hope you all remember that one, what we have seen in the last class. We will be transmitting 1 bit per sample, so that the bandwidth will also be reduced, the channel bandwidth. Along with that one, signaling rate will also be reduced. So for that disadvantage we have overcome by using your delta modulation. But last class also I have stopped at that point. Like we will be having 2 errors in this one. Okay, I'll give you the link of the last class also. Please do go through with that one once again. So I have told already that we'll be having 2 kinds of errors here in this one, in delta modulation. One is your slope overload error or the distortion, and second one is your granular noise. So we'll quickly move on to that particular errors. First we'll see what are the errors that we have and how we are going to overcome this by using your adaptive delta modulation. Fine. See what are the advantages and disadvantages of delta modulation. Once again I am repeating. Advantages are the delta modulation transmit 1 bit per sample, as I've already told. Okay, so delta modulation will be transmitting 1 bit per sample, thus the signaling rate and the transmission channel bandwidth is quite small for your delta modulations, means this can be reduced. Now the second advantage that you are having here is the transmitter as well as the receiver implementation is very simple for delta modulation, and there is no analog to digital converter involved in this delta modulation, because we are transmitting 1 bit per sample. So that easily we can give that sample message and you can quantize that one, and afterwards you can encode that one. So there is no need of your, or there is no operation involved of converting your analog to digital signals, right? Now as I've said, there is a disadvantage. We are having 2 disadvantages in this one, 2 drawbacks. One is slope overload distortion and second one is your granular noise, right? What is the slope overload distortion? First I'll explain this part. Okay, it arises because if there is a large dynamic range input signal. See, these are the steps you have converted, these are the samples. If this input signal is large or its range is so large, then you will be having this kind of error. So what we can say that here, like if the rate of the rise of the input signal is so high, the rate of, I'll repeat it once again, please do make a note. The rate of rise of the input signal is so high that the staircase signal cannot approximate this one. Okay, I'll be repeating it once again. The rate of rise of this input signal is so high so that the staircase signal cannot approximate this one. Thus large error will be occurred, and that particular error is called as your slope overload distortion. This is a slope, this is overload, because this is not approximating your staircase. So if you are having this kind of error, then it is called as your slope overload distortion. I'll repeat it once again. The rate of rise of the input signal is so high that the staircase signal cannot approximate this one. Okay, that's a larger error between your original signal as well as the staircase signal will be happen, and this particular difference is called as your slope overload distortion. Okay, now as to reduce this one, what we have to do, the step size should be increased, right? This step size should be increased from here to here. If I increase my step size, this kind of distortion can be reduced. So as to reduce this error, your step size should be increased when the slope of the input signal is high. If the slope is high, I have to increase my step size. So by this one, I can reduce this particular error. Okay, this was one error. Now you are having one more drawback, that is your granular noise. Now what is granular noise? By seeing this one, you can easily tell, right? So this noise occurs when the step size is too large. Now if you are having your step size is too large, here what we have said, rise of the input signal is very high. If this input signal is very high, this slope overload distortion will be occurring. If the step size is too large, then you will be getting your granular noise. So this noise occurs when the step size is too large when compared to the small variations in the input signal. When you are having small variations in the input signal, so your step size should be small over here, right? So as to reduce, this is called your granular noise. I'll repeat it once again. This noise occurs when the step size is too large when compared to the small variations in the input signal. That is, for very small variation in the input signal, the staircase can be changed by the larger amount. Okay, so based upon your step size. So these occurs is between your input as well as the approximate output value. So for this one, this kind of error is called as your granular noise. So what you have to do, as to overcome these error, the step size delta is made so adaptive to the variations in the input signal that you can also call it as x of t. This is the x of t. So what you are doing over here, as to overcome these errors, the step size delta, you already know what is the step size. This, okay, this step size delta is made adaptive, means you can change, or it can be changed according to the input signal. Either if it is having slope is too larger, this or your step size will be increased. If the input signal is not that much variant, your step size should be decreasing. So what we have to do, this delta, that is your step size, should be adaptive to the variations in the input signal. Whatever the signal you are getting, that this delta should be adaptively variant. So that is what we call as adaptive delta modulation. So these two errors can be reduced by using your next pulse code modulation technique, and that is called as your adaptive delta modulation technique. Fine, I hope you are clear. So here is the explanation of how your slope overload distortion can be, what actually it is, and how they can be what you are going to go through in that one. It is also called as startup error, because you had here in the starting part, right, and the next part, the granular noise, it is also called as haunting error. So this was about your error, whatever I have already discussed. I'll be sharing the notes with your people. Please go through with that one. Okay, so if you are larger, the step size is required to accommodable with the dynamic range of input signals as to reduce the slope overload error, as well as the small steps are required to reduce the granular noise. So all this can be done by using your adaptive delta modulation is used to overcome these errors. Now we'll move on what is actually this adaptive delta modulation. Fine, I'll just read it out what actually the operating principle is involved in this, and also I'll tell you what actually the main block you are involving in this adaptive delta modulation as to overcome these two kind of errors, right? As to overcome the quantization errors due to the slope overload as well as the granular noise, the step size delta is made adaptive to the variations in the input signal of x of t, as I've already told you. Okay, so particularly in the steep segment of a signal, steep segment means at the higher part of your signal x of t, this is your input signal, the step size is increased. So here what you have to do, here your step size is to be increased. This is the steep signal of your x of t, right? This is the input signal. Now what you have to do, then the method, then when the input signal is varying slowly, the step size should be reduced. Now here when the input signal is, now here it is varying, it is decreasing, so automatically your step size should be decreased over here. So this can be done by using your method called as your adaptive delta modulation. This can be taking continuous changes in the step size or the distributive changes in the step size. So what this adaptive delta modulators or the modulation will be doing, they will be making the continuous changes in the step size, or they will be doing the discrete changes in the step size accordingly. If the input signal is increasing, the step size will be increased. If this input signal is decreasing, then the step size will be decreased. So by using that one only, your what we can say, these two kind of noises or the disadvantages can be reduced, that is slope overload as well as the granular noise. Let's see what the transmitter and the receiver you are having here. This is the transmitter. Okay, here you will be having a logic step size control signal. Okay, in this one it is similar to that of your delta modulation. Okay, the same 1-bit quantizer you are having. What we have said in the adaptive delta modulation, 1 bit per sample you are transmitting. So here same modulator we will be using, plus along with that one we will be using a logic for step size control, because we have to control the step size according to your input values. So the logic for the step size control block is added in your adaptive delta modulation technique. So the step size increases or decreases accordingly to the specified rule depending upon 1-bit quantizer. Depending upon this one, if you're quantizing depending upon this 1-bit quantizer, like if your step size is 1, your step size will go increasing. If quantizer is giving output as 0, your step size will be decreasing. So this is how it will be moving on. So I'll repeat it once again. The step size increases or decreases according to the specified value or the rule depending upon the 1-bit quantizer. For example, if 1-bit quantizer is high or 1, okay, then the step size may be doubled for the next sample. Okay, first in case first it is already, if there is no value, it will be 1. Then again quantizer is giving you the answer as 1. So what step size will be doing? It will be doubling, means two same samples will be getting 1 and 1. Okay, if 1-bit quantizer is low or the 0 if it is giving as the output, then the step size may be reduced by 1 step. Your step size will be reduced by 1 step. So this is how you will be working. In the receiver part, what you will be seeing here? In the receiver part, the first portion is producing the step size for each incoming bit. Whatever the input bits that you are getting, first they will be getting the step size. Then it is then applied to the second portion, that is your receiver block, and second portion of the receiver block, which will be building up the staircase waveforms depending by giving what you can say a time delay. Then it is given to a low pass filter as to smoothen this particular staircase waveform as to extract your original input message signal. Okay, I hope you are clear with this one. See, again I'll explain. See, the working operation is similar to that of your delta modulation. Only thing is that you will be adding here extra logic for step size control. So whatever the input signal you have got here, that will be given to the 1-bit quantizer. Again from that one you will be getting delay of 1 second or something. Then again it is given to the 1-bit quantizer, so that 1 sample per head, 1 sample per second or 1 sample will be given. Okay, then after that this will be given to the logic for the step size control. So what it will be doing, depending upon the output of the 1-bit quantizer, the step size will be increased or decreased. Here already one example is given. For example, if 1-bit quantizer output is high or 1, then the step size may be doubled for the next sample. If the 1-bit quantizer, this one, is low, then the step size may be reduced by 1 step. Okay, then it will be showing the waveform of the adaptive delta modulator and the sequence of the bits at the transmitter. In the receiver, what we will be doing, first we will be deciding the step size, like how much it will be the step size. Then it is given to the time delay, because we are taking 1 sample per time second, okay, for every second. Then it is given to a low pass filter, where it will be smoothening your signal, smoothening your staircase waveform, right, and it will be extracting your original message signal. So this is how you will be extracting your original message signal, right. So this is how the waveform of the adaptive delta modulation. These are the staircases that are obtained by the output which is given by your 1-bit quantizer. At the output side, what will be by using the low pass filter, we will be again reconstructing our original message signal. If the input is high, so this is how you will be giving the, if 1-bit quantizer will be giving the signal as 1, so this is how it will be moving on. If it is giving 0 as the output, then step size will be decreasing. So this is how you will be moving on. So this was about your adaptive delta modulation technique, right? So I hope you are clear with the adaptive delta modulation. Why actually we have moved on for the adaptive delta modulation. First thing is delta modulation, where we are giving the time delay of 1 sample per second. Then in that one we are having 2 errors, granular noise and slope overload error. As to reduce that particular errors, we are going for adaptive delta modulation, where it will you are what you can say, adaptively or instantly your step size should be changed according to your input signal. Correct. So now we'll see what are the advantages of your adaptive delta modulation. Very first advantage is that the signal to noise ratio is better than ordinary delta modulation because of the reduction in slope overload distortion as well as your granular noise. Correct. We had what are the ADM has certain advantages over DM. That is, adaptive delta modulation is having much more advantages than of your delta modulation. So the signal to noise ratio is better than that of your ordinary delta modulation because it is reducing your both errors. One is slope overload as well as the granular noise. Second comes to, because of variable step size, the dynamic range of the ADM is wide. Correct? Because we are having a variable step size over here. Now utilization of the bandwidth is better than delta modulation because we are having variable step size. Accordingly, we can have proper utilization of the bandwidth in the delta ADM. Okay, now plus other advantage of delta modulation are only 1 bit per sample is required and simplicity of implementation of transmitter and receiver, because we are using only 1 bit per sample, so it is very simple to implement for both transmitter as well as the receiver. So these are the advantages of your adaptive delta modulation. I hope you are clear with this all. So I hope you are all clear with the all pulse code modulation technique. Now this is the last topic of your first unit. So that is your time division multiplexing. So I'll just finish it out. It is a very small topic. We'll just wind it up with this one. So what actually time division multiplexing is. So I'll briefly explain about the time division multiplexing, a small topic of this first chapter, and I'll show you the block diagram of your TDM, how it will be working. Fine. So let's start this one. So the sampling theorem provides the basics of transmitting the information which is contained in the band limited message signal as a sequence of m of t time uniformly at the rate it is usually slightly higher than that of your Nyquist rate. Okay. Now, as an important feature of the sampling process is your conversion into time. Correct. Now see what we are doing in this one. In digital communication, we are converting your message signal or the analog signal into a digital signal. Correct. Now for that one we require the sampling first. So we have seen the sampling theorem also, Nyquist rate, because as to convert that one, it should be your message signal should be slightly greater than of your Nyquist rate. So we have given a rate in the data of 2 bandwidth 2W. Correct. So for all this process, for all this information that you have to convert your analog to digital signal, as to get all these proper message signals into sequence of samples, that too into uniformly, we require some sampling process, that too in conversion of time. Of course, right? It is an important feature of the sampling process is a conversion of time, that is transmission of the message samples engages communication channel for only a fraction of sampling time on the some periodic basis only. Now we actually require like how many signals or how many samples should be given in that particular time shared basis. So what we are doing, we are independently sending the messages, making some samples in that particular time. So we hereby what we will be obtaining a time division multiplexing system, which will be enabling us to joint utilization of a common communication channel by a plurality, means number of independent messages can be sent at a time with some time slots. Yes, I hope you understood. What we are doing now, simply I'll explain. Like, we have to convert the analog signal into the message signal, right? For that one we require sampling process. Correct? First one is sampling process. Now after converting, you have to sampling. So which signal or which bit has to be given at which time, we don't know. I have to convert that into particular time intervals. So for that one we are going for the time division multiplexing. We are dividing particular time, we are multiplexing and sending one by one messages. Okay, we sample the messages, and this is how your overall utilization of the communication channel can be done. So I'll repeat it from here, which is very important point here. We thereby obtain a time division multiplexing system which enables the joint utilization of a common communication channel by a plurality, means number of independent message sources without mutual interference among them. Yes, because if you are having for every time, first second is this message sample has to be sent, for second one, third one, fourth one, because we are dividing in the time. If you are not having this time division multiplexing, all the message signals will be sampled and will be sent at a time. So due to that one we will be getting the interference. So as to reduce that mutual interference, we are going for the time division multiplexing. Right. So before I go explain about what actually time division multiplexing block diagram will be having, I'll show you this one first. So it will be consisting of the low pass filters first, okay, which will be having anti-aliasing filters. So in that one, first the message signals will be given to the low pass filters, and that filters will be giving to a commutator. So from that commutator, this will be given to the pulse modulator, where you will be adding the clock pulses, that your carrier signals will also be added. Then after that, by using a communication channel, whatever the channel, either wired or wireless, it is given to the communication channel to the demodulator, that is nothing but your receiver part. Again you will be having clock pulses, nothing but your carrier signals. Okay, and a decommutator, compulsory synchronization should be there. Okay, whatever at which time, what is message signal and the sample signal you have given at that particular time, you will be setting the particular time, that synchronization should be matched. Okay, then from that one decommutator, again you will be giving it to the low pass filters. From there you will be getting the message signal, original message signal at the output side. Okay, these are the blocks which are involved in your TDM, that is time division multiplexing. Now I'll explain you one by one. See here. So the concept of TDM, whatever we are going to discuss, that I have shown already in that figure, right? Now each input message signal is first restricted to a bandwidth by a low pass anti-aliasing filter, as to remove the frequencies that are non-essential to an adequate signal representation. Now why we are using this low pass filter first? Whenever I am saying, please do note down. Okay, first part we are having low pass filter. Your message signals are given to the low pass filter, because these filters will be restricting the bandwidth which are not necessary for our communication, right? So by using the anti-aliasing filters, this will be removing the frequencies which are not necessary for your adequate signal representation. So first extra frequencies or non-essential unimportant frequency will be removed by using your low pass filter, right? From here, this part. Now the removed frequencies, this will be given to your commutator, right? These communicator or the commutator, the low pass filter outputs are then applied to the commutator, which are usually independent, using the electric switching circuitry or the electronic switching circuitry. It means that the function of the communicators are two. Okay, it has two functions. First function is to take the narrow sample of each of the n message or the n input message at the rate of fs, that is sampling frequency rate, that is slightly greater than of your 2w. This is the sampling theorem, where fs is greater than that of 2w. So this is your cutoff frequency, which w we will be calling as. The first function of your commutator is to take the narrow sample of each input signal, because if you will having n number of signals, for n number of signals, for each and every sample, it will be taking the narrow sample of each of n input messages at the rate of fs that will be greater than of 2w. That please make a note, the fs is greater than 2w, where w is the cutoff frequency of your anti-aliasing filter. That is the first function of your commutator. What it will be doing? It will be taking the narrow samples, and its rate should be what should be the rate? fs should be greater than of your 2w. That is the first one. Okay, first function of your commutator. Now the second function of the commutator is to sequentially interleave these samples inside the sampling interval Ts. Now what it should be doing, it will be sequentially interleave the samples, means they should be having some time gap between these samples, okay, or the sampling time interval should be given between these samples, and the time interval is your Ts. So these afterwards what the function, the essence of the time division multiplexing operation is done over here. Okay, indeed this latter function is the essence of your time division multiplexing operation. Now following the communication process, the multiplexer signal is applied to the pulse modulator. You have done here multiplexing. Okay, you have first divided them into a number of samples, and the sampling should be fs greater than of 2w, where w is the cutoff frequency. Then afterwards second function is you will be giving the time interval, that is your Ts. For every sample you should be giving you should be interleave a time, that is your time interval Ts. Now following the function, after this communicator output should be given to the pulse modulator. So the purpose of which is to transfer the multiplexer signal into the form of suitable for transmission over a communication channel. I'll repeat this once again. You can easily grasp this point, why we use a pulse modulator. What actually modulator is nothing but you have to combine both message signal as well as the carrier signal. Either of the pulse modulators you can take depending upon your particular application. The main purpose of this is to transform this multiplexer signal into the suitable form as to transmit it over to a communication channel, because you have to transmit it from transmitter to the receiver. It should be some process has to be done, means some modulation has to be done. You can use any modulation, either pulse modulation, we have said PCM, DM, ADM or DPCM, any one. So the purpose is only one, is to transform the multiplexer signal into a form suitable for the transmission over a communication channel, right? It is clear that use of the TDM introduces a bandwidth expansion factor n, because the scheme must squeeze n samples derived from the n independent message sources into the time slot equal to one sampling rate. Okay, so the thing what happens here, the bandwidth expansion factor will be, it is clear that TDM introduces a bandwidth expansion factor, because here what we will be having, we are taking the n number of samples which are independent from your message source, and that particular samples are giving a particular time slot which are equal to the sampling interval also. So this all will be introducing a new factor that is called as bandwidth expansion factor. So depending upon that particular factor only we can get to know how many samples are there, or how many independent samples are there, and in which time slot. They are taking 2 seconds of time slot for getting one particular sample, or 3 seconds of time slot. Depending upon this expansion factor, you will be getting how many samples are there in that particular slot of time. Okay, now at the receiving end of your system you will be having a pulse demodulator first, then you will be demodulating yours, or means separating your carrier along as well as a message signal. Then afterwards you will be giving it to the low pass filter for the reconstruction, right? Then you will be having, and importantly you will be you have to note that synchronization is very important both at the transmitter as well as the receiver side. So this synchronization is essential for the satisfactory operation of the system. In case if there is no synchronization between the commutator and the decommunicator, there is you will not be getting the proper output signal. Okay, what output signal in the sense, whatever the message you have given at the transmitter, that proper output cannot be obtained at the receiver. So synchronization is very important. So this synchronization is very essential for the satisfactory operation of the system. The way this synchronization is implemented depends naturally on the method of pulse modulation used to transmit the multiplexer sequences of samples. I repeat, what happened, this synchronization depends upon the pulse modulation scheme that we are choosing for your transmission of your multiplexer signal to the through a particular channel. So depending upon the particular modulation scheme whatever you are choosing, so synchronization depends upon that modulation scheme, right? So the TDM system is highly sensitive to the dispersion in the common channel, that is 2 variations of the amplitude with the frequency, or lack of proportionality of the phase with the frequency. So according to all this one, what we can say that it is necessary to ensure the satisfactory operation of the system. So why this TDM is actually used, as to get the proper satisfactory operation of all your system, we require this TDM. Because if TDM is not there, time slots will not be given. If time slots are not there, you will be getting a mutual interference, and if interference occurs, you won't be getting the outputs properly. So the TDM is very important. Then this TDM signal is given to the commutator. This commutator is output is given to the modulator. Depending upon your particular application, this any modulation technique you will be using, that transmitted signal will be given to the receiver through a particular channel, and the demodulator, again you will be separating your demodulating your message signal, that is given to the decommunicator. From there it will be given to the low pass filter as for the reconstruction of your message signal. So this was about your TDM. So TDM is immune to the non-linearities in the channel as a source of the crosstalk. So the reason of the this behavior is that different messages are not simultaneously applied to the channel. Okay, so we have to make sure that different messages are what we can say should be given at some time gap. Okay, so I hope you are clear with this TDM and adaptive data modulation. So this was about your first unit. I hope I have covered all the topics in the first unit. So please go through the videos. Okay, in case of any doubts, please do let me know. Along with that, please make the notes also. Okay, I'll wind up the class here itself. Thank you.